Hello everyone, welcome to RN tutorials. So in this video that is related to the mechanics of fluids and hydraulic machines, we are going to discuss about the loss of energy due to the enlargement in pipe, which is mainly considered as a minor loss. And mainly we have two types of the losses. One is major loss and another one is minor loss. So major losses are mainly due to the frictional resistance offered by the internal surface of the pipe, and the minor losses are due to the enlargement in pipe, contraction in pipe, and the loss due to bend section, and loss due to various pipe fittings, and loss due to sudden obstruction in the pipe. So because of enlargement here, we'll be facing minor losses which are less compared to the frictional loss, and these losses are considered when we will be considering the short length pipe. So when it is longer length pipe, the minor losses can be neglected as the value compared to the major loss. So when it is the shortest pipe, for that pipe we need to consider both major and minor. So whenever the loss due to the enlargement taking place, we need to know how to find out the value by using an expression. Okay, so that expression how to derive, now we are going to discuss. Okay, so for that I want to assume a smaller diameter pipe, okay, which is connected to another pipe which is having larger diameter, so which shows the enlargement in the cross sectional area of the pipe, okay, due to which we will be facing the loss of energy. Here assume if liquid is flowing through this pipe with a particular velocity v1. So when it comes to the larger diameter pipe, so in this case due to this sudden abrupt change in the cross sectional area of the pipe, the water flow cannot adjust itself suddenly throughout this cross sectional area of the pipe. So because of that, and again due to the velocity variation from this cross sectional area smaller, assume it as a1 smaller diameter and a2 larger diameter, so automatically velocity variation takes place. Okay, so due to that velocity variation also, the water will be separated from the boundary of the second pipe, and slowly it will be reaching the boundary of the larger pipe, that is the second pipe, which is due to the sudden change in the cross sectional area which causes the velocity variation, and then it will try to flow in a second pipe throughout, occupying the area of the pipe. Okay, so like this the liquid can be separated from the boundary of the pipe due to the variation in the velocity which is due to the variation in the cross section area. Okay, whatever the region formed where the fluid liquid flow is separated from the boundary of the pipe, so here the water molecules will enter and randomly they will move in this region, so which will form the eddies in this region. So due to these eddies, again the loss of energy takes place. So mainly these eddies formation due to the velocity variation and due to the variation in the cross sectional area causes the loss of energy. Okay, so this loss of energy we need to find out. Okay, so for finding this loss of energy due to the eddies formation which are due to the variation in the velocity, we need to apply, okay, for deriving an expression we have to apply energy equation which is Bernoulli's equation. Okay, and second one we need to apply momentum equation, momentum principle. Why? Because the velocity variation is taking place means momentum variation also takes place, so both conditions we need to apply for the flow of the liquid. So by applying these two conditions we can derive an expression for finding the how much the loss of energy is going to take place due to the uh, enlargement in the cross sectional area of the pipe. So first I want to apply the Bernoulli's equation. First I want to apply Bernoulli's equation. Okay, so generally we know that the statement of the Bernoulli's equation is that whatever the energy available at section 1, total energy sum of the three energies at section 1 should be equal to the total energy which is the sum of the three energies at section 2, even the cross sectional area variation takes place. Okay, so here for that I want to assume at section 1, assume this here as section 1 and here in the second pipe as section 2. Okay, at section 1 assume pressure P1 is acting in the direction of the flow, and section 2 P2 is acting in opposite to the direction of flow, and v1 is the velocity, a1 is the area section 1, and here also assume v2 is the velocity and a2 is the area of the pipe. Okay, so by assuming these conditions we can apply the Bernoulli's equation, which states that total energy at section 1 should be equal to total energy at section 2, and this condition is when there is no loss is taking place. But here when it is moving from section 1 to section 2, certain loss of energy is taking place. That loss I want to assume it as He. Okay, so this much of the energy loss is taking place whenever it is moving from 1 to 2, so that whatever the energy available at section 1 cannot be equal to the energy available at section 2. So whenever these two becomes equals means when we add this energy loss of energy to the energy available at section 2, then it can be equal to the section 1. Similarly here we need to add loss of energy to the enlargement, that is He. Okay, so in the equation form how can we write means based upon knowing the Bernoulli's equation, which is P1 by rho g plus V1 square by 2g plus Z1 is equal to P2 by rho g plus V2 square by 2g plus Z2 and plus loss of energy due to the enlargement. So based upon the horizontal pipe we are considering at any datum line, the Z1 can be equal to Z2. Okay, then this Z1 here, this Z2 gets cancels, so finally He is equal to, we can write it as P1 by rho g. So keep the He on the right side and take all the terms to the left side, then the equation will be P1 by rho g minus P2 by rho g, okay, and plus V1 square by 2g minus V2 square by 2g. So this expression will be getting when we try to write He is equal to, assume this equation as 1. Okay, this is up to applying the Bernoulli's equation. Next we go for application of momentum principle. Okay, momentum principle. So how can we apply the momentum principle means, what is the momentum principle? The momentum principle states that the total force or net force acting on the liquid can be equal to rate of change means change with respect to time, that is rate of change of momentum. So the rate of change of momentum should be equal to the net force acting on the liquid. So this rate of change of momentum can be written as, this dmv can be considered as the change in momentum at the 2 points. Change means we need to consider the difference of the two momentum. So here we can apply momentum at section 2, momentum at section 1. So the change means momentum at 2, so that is final momentum minus initial momentum, we can write it as. So here I want to write change in momentum means m2 v2 minus m1 v1 by dt means we can write it as time. For any time how much the rate of change in momentum is taking place we need to write. Okay, this equation again can be modified as, so look at here, the net force acting on the liquid again equal to rate of change of momentum can be written as, the mass can be written as from the density formula. What is the density formula? Density formula is mass by volume. Okay, so the mass can be written as rho into volume. Okay, so in place of mass I want to write rho into volume 2, that means volume in the second pipe, into v2 square, I want to write it as per time t, minus in place of m1 we can write as rho volume 1 into v1, here not square, sorry, okay, v1 by t we can write it as. Okay, and again when you observe volume per unit time, here also volume per unit time. So volume means how much the amount of the liquid is flowing per unit time, which is known as flow rate or discharge. So in place of volume per time we can write it as rho into q2 into v2 minus rho into volume per time again q1 into v1. Okay, so already we know that q discharge is equal to area into velocity. So again write it as place of q2 a2 v2 into v2 minus rho a1 v1 into v1. Okay, so finally we can write this equation as rho a2 v2 square minus rho a1 v1 square. So again I want to modify this equation by using continuity equation. So by continuity, from continuity equation we can write a1 v1 is equal to a2 v2. Okay, so a1 I want to write a1 is equal to a2 v2 by v1. So I want to substitute this a1 is equal to in the above equation, that is rate of change in momentum. F net is equal to net force is equal to rate of change. In place of a1 we have to write, so rho a2 v2 square minus rho a1, in place of a1 write a2 v2 by v1 into v1 square. Okay, 1 v1 square gets cancels. So finally we can write rho a2 v2 square minus rho a2 v1 v2 we can write. So take rho a2 common, so rho a2 of v2 square minus v1 v2 we can write the equation as. So that is the net force acting. Assume this equation as 2. Okay, so this is the rate of change of momentum modified. So this is F net. So again I want to write net force acting on the liquid. So the net force acting on the liquid we need to analyze how many number of forces will be acting on the liquid. So come to the figure again. So when you are considering different pressures, so due to that pressure certain amount of the force will be acting on the flowing liquid. So at section 1 P1 is the pressure acting. So the force due to the pressure at section 1 we have to consider. Similar at section 2 P2 is acting. Again we need to consider force due to pressure at section 2, and at the same time wherever the eddies formation is taking place section, so at this section this eddies water particle moving randomly can also maintain certain amount of the pressure that I want to assume it as a P dash. So this P dash will be acting in this particular area region. Okay now, so that area I want to assume A dash. So from the figure itself we can write this A dash. So these two areas can be obtained by subtracting a2 minus a1. So when you subtract a1 from a2, so this area will be getting, so area is equal to automatically a2 minus a1. So total three pressures acting, so the three forces due to the pressure we need to consider. Okay, and here again listen here, the force due to pressure at section 1 is in the direction of flow, force due to pressure at section 2 opposite to the direction of flow, and force due to pressure in the eddies formation will be again in the direction of the flow only. Okay, why? Because after moving in this region again this molecule will try to mix with the water, so this again flows to the direction of the flow only. Okay, so that is also positive we need to consider, remember. So now I want to write force due to pressure at section 1 as P1 A1 pressure and area, at section 2 minus P2 A2 because it is opposite direction, and similarly plus P dash A dash because again it will act in the direction of the flow. So I want to write A dash is equal to, already we have analyzed as A2 minus A1, and by the experimental observations it is observed that P dash is equal to P1. So again the F net can be written as, net force can be written as P1 A1 minus P2 A2 plus P1 of A2 minus A1 we can write. So now open the bracket, P1 A1 minus P2 A2 plus P1 A2 minus P1 A1. So this negative P1 A1 term, positive P1 A1 term gets cancels. So again here we can write net force acting on the liquid is equal to, when you take the A2 as common we can write it as P1 positive minus P2 negative. Okay, so again assume this equation as 3. So as per the momentum principle again 3 equation can be equal to 2 only, or 2 is equal to 3 we can write it as. So write again both the equations equal, A2 of P1 minus P2 is equal to rho A2 of V2 square minus V1 V2. Okay, so this A2 gets cancelled. take the P1 to the left side, P2 by rho is equal to, we'll be getting V2 square minus V1 V2. So I want to take the G on both sides in the denominator. So when you keenly observe this, assume this equation as 4. Okay, this P1 by rho G minus P2 by rho G we can see in the first equation. So in this first equation we have P1 by rho G minus P2 by rho G term, which will be P1 minus P2 by rho G only. So in place of this term we try to like the fourth equation, write this fourth equation. So that means substitute 4 in first equation. So HE is equal to, we'll be getting in place of P1 minus P2 by rho G as V2 square minus V1 V2 by G plus V1 square minus V2 square by 2G. So take the LCM again here. When you take the LCM, HE is equal to whole by 2G will be getting. So here G is having, when you multiply 2G, GG gets cancelled but the 2 remaining. So here we will be getting 2 V2 square minus 2 V1 V2, and here when you multiply 2G both gets cancelled. So as this term will be getting V1 square minus V2 square. Okay, so 2V2 square minus V2 square will give you V2 square minus 2 V1 V2 plus V1 square by 2G. When you keenly observe this one, A square plus B square minus 2AB in the form of A minus B whole square it is looking like. So we can write it as V1 minus V2 or V2 minus V1 whole square by 2G, which will be HE is equal. So this is the final equation, which is in terms of the velocity, which will give you the loss of energy due to the sudden enlargement in pipe, which is again due to the velocity variation is taking place due to the cross-sectional area variation is taking place. So in terms of the velocity, we have derived the equation, which is the simplest equation by which we can find out the loss of energy due to the enlargement in the pipe. So I hope you understand. By applying simple two conditions, one is Bernoulli's equation and another one is momentum principle, we can derive this equation. Okay, so thanks for watching my video again. Please subscribe to my channel, please share my video with your friends, and once again thanks for watching my video. Thank you all.